Welcome to the Plutus Pioneer Program. We are very excited to have so many of you participating. I'll start by saying a couple of things about the organization. So we'll have the first lecture today, Thursday, but the plan is to, starting next week, switch to a different rhythm. So we'll have lectures coming out on Tuesdays, and then we'll have a Q&A session, a live Q&A session on Thursdays. And because there are so many of you, it's unfortunately not possible to be as interactive as I'd like it to be. So it would be great if all of you could use the Discord server to help each other answer questions and solve problems. I mean, we will do what we can, my colleagues and myself, to answer questions and help. But with the sheer number of participants, it's just not possible to pay as much attention to every individual as we would like. So thank you for helping out. As for the content, so the idea is to really give a thorough introduction to Plutus, explain the underlying concepts, look at various types of contracts, look at how we can test contracts in the playground or also offline locally, talk about native tokens, how to control minting and burning of native tokens in Plutus. And we'll also look at how to deploy a Plutus contract and write a backend for a Plutus contract. Plutus learning is not easy, unfortunately. So you have to be aware that the course probably won't be easy. And there are a variety of reasons for that. So one is that Plutus uses the so-called eUTXO model. I'll explain in much more detail what that means later in this lecture. And that is different and less intuitive than the Ethereum method for doing smart contracts. It has a lot of advantages, the eUTXO model, but it also requires a new way of thinking about smart contracts. So that's one thing. And that's before we even start with the language itself. Then, of course, Plutus is brand new and still under rapid development. So probably during the time of the course, there will be significant changes. So we'll often have to update the dependencies on the main Plutus repository. And it might be that contracts that compile at the beginning of the course won't compile any longer at the end of towards the end of the course, because there have been some syntax changes. In addition to that, tooling is not ideal yet. So those of you who have experience with Haskell and know about the Haskell tooling will notice that in the presence of Plutus, some of the tooling is not as pleasant as you may be used to it being from doing Haskell. So sometimes it's a bit painful, so it's not as easy to get access to syntax of functions or to documentation from the REPL, for example. And it's not even very easy to build Plutus in the first place. So your best bet is probably using Nix. You can also try Cabal and Stack or Docker. Actually, the Plutus team will provide a nice Docker image at some point, so maybe that will then be the easiest option. But yeah, it's not totally trivial to get Plutus to compile in the first place. Then, of course, Plutus is Haskell more or less. So on top of the other problems, you first have to have a firm grip on Haskell in order to do Plutus. And obviously, in the 10 weeks of course time, I won't have time to first do a proper, thorough Haskell course. The Haskell courses that I did in Greece, on Barbados, in Ethiopia, and then last year virtually in Mongolia were full-time courses, 10-week full-time courses, 40 hours a week. And even in those courses, we didn't cover everything that you will need to to fully understand Plutus. Of course, we also covered things that are irrelevant for Plutus, so it's not as bad as it sounds. But nevertheless, there's quite some Haskell that you need. And I won't have time to thoroughly explain everything. I try to explain the special concepts that you need for Plutus, obviously. And whenever there's a special need, when I see that a lot of you are struggling with something, then obviously I'll take the time to explain that topic in more detail. So unfortunately, I won't be able to spend as much time teaching Haskell as I'd like to, because obviously I mostly want to do Plutus. But we did record our Mongolia Haskell course, and we have started editing the videos and making them nicer and more concise. And what we have, we'll publish here for you on the Discord server, so that if you're struggling with Haskell and would like an introduction that's much slower paced, then you can give those videos a try, and maybe they help with the Haskell problems you might have. Another problem is that Plutus is brand new, which of course is also very exciting, but it also means that you and I and the Plutus team are the first people ever in the history of humanity that write Plutus code. So if you learn another programming language and you get stuck or have a problem, then normally you can just go to Stack Overflow or Google, and often you'll be lucky and find an answer. So because we are the first, you won't have that option. So we have to figure it out while we go along. As for the curriculum, I told you what topics I want to cover, but I also consciously made the decision not to publish the curriculum in advance, because I want to be flexible and be able to react to your feedback. So if I see that a lot of you are struggling with a certain concept, then we can spend more time on that. Or if I see that a lot of you are very eager to learn some specific thing, then we can do that. So I want to keep it flexible and see how it goes, and then react to feedback to make it as valuable as possible for every one of you. One of the most important things you need to understand in order to write Plutus smart contracts is the counting model that Cardano uses. And that is the so-called EUTXO model, which is an abbreviation for Extended Unspent Transaction Output Model. The UTXO model, without being extended, is the one that has been introduced by Bitcoin. But there are other models. Ethereum, for example, uses a so-called account-based model, which is what you're used to from a normal bank, where everybody has an account and each account has a balance. And if you transfer money from one account to another, then the balances get updated accordingly. But that is not how the UTXO model works. Unspent transaction outputs are exactly what the name says. They are transaction outputs, that is, outputs from previous transactions that happened on the blockchain that have not yet been spent. So let's look at an example where we have two such UTXOs. One belonging to Alice, 100 ADA, and another one belonging to Bob, 50 ADA. And as an example, let's assume that Alice wants to send 10 ADA to Bob. So she creates a transaction. And a transaction is something that has inputs and outputs. Can be an arbitrary number of inputs and an arbitrary number of outputs. And an important thing is that you can always only use complete UTXOs as input. So if she wants to send 10 ADA to Bob, she can't simply split her existing 100 ADA into a 90 and a 10 piece. She has to use the full 100 ADA as input. So by using the UTXO of 100 ADA as input to a transaction, Alice has now spent that UTXO. So it's no longer a UTXO, it's no longer unspent, it's been spent. And now she can create outputs for a transaction. So she wants to pay 10 ADA to Bob. So one output will be 10 ADA to Bob. And then she wants her change back. So she creates a second output of 90 ADA to herself. And so this is how, even though you always have to consume complete UTXOs, you can get your change back. So you consume the complete UTXO, but then you create an output for the change. And note that in a transaction, the sum of the input values must equal the sum of the output values. So in this case, 100 ADA go in and 10 plus 90 ADA go out. This is strictly speaking not true. There are two exceptions. The first exception is transaction fees. So in the real blockchain, for each transaction, you have to pay fees. So that means that the sum of input values has to be slightly higher than the sum of output values to accommodate for the fees. And the second exception is the native tokens that we have on Cardano. So it's possible for transactions to create new tokens, in which case the outputs will be higher than the inputs, or to burn tokens, in which case the inputs will be higher than the outputs. But that is a somewhat advanced topic, how to handle minting and burning of native tokens in Plutus, and we'll come back to that later in the course. So for now, we'll only look at transactions where the sum of the input values equals the sum of the output values. So this is a first example of a simple transaction, and we see that the effect of a transaction is to consume unspent transaction output and to produce new ones. So in this example, one UTXO has been consumed, Alice original 100 ADA UTXO, and two new ones have been created. One 90 ADA UTXO belonging to Alice and another 10 ADA UTXO belonging to Bob. Let's do one other example, a slightly more complicated one, where Alice and Bob together want to pay 55 ADA each to Charlie. So they create a transaction together, and as input, Alice has no choice. She only has one UTXO, so she uses that one. And Bob also doesn't have a choice because neither of his two UTXOs is large enough to cover 55 ADA. So Bob has to use both his UTXOs as input. This time we need three outputs. One, the 55 plus 55 equals 110 ADA for Charlie, and then two change outputs. One for Alice's change and one for Bob's change. So Alice paid 90, so she should get 35 change, and Bob paid 60, so he should get 5 change. One thing I haven't yet explained is under which conditions a transaction can spend a given UTXO. Obviously, it wouldn't be a good idea if any transaction could spend arbitrary UTXOs. If that was the case, then Bob could spend Alice's money without her consent. So the way it works is by adding signatures to transactions. So for our first example, our transaction 1, because that consumes an UTXO belonging to Alice as input, Alice's signature has to be added to the transaction. And in the second example, because there are inputs belonging to both Alice and Bob, both Alice and Bob have to sign that transaction, which incidentally is something you can't do in Daedalus. So you would have to use the Cardano CLI for complex transactions like that. Everything I've explained so far is just about the UTXO model, not the extended UTXO model. So this is all just a simple UTXO model. And the extended part comes in when we talk about smart contracts. So in order to understand that, let's just concentrate on one consumption of a UTXO by an input. And as I just explained, the validation that decides whether the transaction that this input belongs to is allowed to consume that UTXO in the simple UTXO model relies on digital signatures. So in this case, Alice has to sign the transaction for this consumption of the UTXO to be valid. And now the idea of the extended UTXO model is to make this more general. So instead of just having one condition, namely that the appropriate signature is present in the transaction, we replace this by arbitrary logic. And this is where Plutus comes in. So instead of just having an address that corresponds to a public key and that can be verified by a signature that is added to the transaction, instead we have more general addresses that are not based on public keys or the hashes of public keys, but instead contain arbitrary logic that can decide under which condition this specific UTXO can be spent by a transaction. So instead of an address going to a public key, like Alice's public key in this example, there will be an arbitrary script, a script containing arbitrary logic. And instead of the signature in the transaction, the input will justify that it is allowed to consume this output with some arbitrary piece of data that we call the redeemer. So we replace the public key address, Alice in our example, by a script, and we replace the digital signature by a redeemer, which is an arbitrary piece of data. Now the next question is, what exactly does that mean? What do we mean by arbitrary logic? And in particular, it's important to consider what information, what context the script has. So there are several options. And the one indicated in this diagram is that all the script sees is the redeemer. So all the information the script has in order to decide whether it's okay for the transaction to consume this UTXO or not is looking at the redeemer. And that is the thing that Bitcoin incidentally does. So in Bitcoin, there are smart contracts. They are just not very smart. They are called Bitcoin script. And Bitcoin script works exactly like this. So there's a script on the UTXO side and a redeemer on the input side. And the script gets the redeemer and can use the redeemer to decide whether it's okay to consume the UTXO or not. But that's not the only option. We can decide to give more information to the script. So Ethereum uses a different concept. In Ethereum, the script basically can see everything, the whole blockchain, the whole state of the blockchain. So that's like the opposite extreme of Bitcoin. Bitcoin, the script has very little context. All it can see is the redeemer. In Ethereum, the scripts, the Solidity scripts in Ethereum can see the complete state of the blockchain. So that enables Ethereum scripts to be much more powerful. So they can do basically everything. But it also comes with problems. Because the scripts are so powerful, it's also very difficult to predict what a given script will do. And that opens the door to all sorts of security issues and dangers, because it's very hard to predict for the developers of an Ethereum smart contract what can possibly happen, because there are so many possibilities. So what Cardano does is something in the middle. So it doesn't offer such a restricted view as Bitcoin, but also not such a global view as Ethereum, but instead chooses a middle way. So the script can't see the whole blockchain, can't see the state of the whole blockchain, but it can see the whole transaction that is being validated. So in contrast to Bitcoin, it can't just see this one input, the redeemer of this one input, but it can see that and all the other inputs of the transaction and also all the outputs of the transaction and the transaction itself. And the Plutus script can use that information to decide whether it's okay to consume this output. Now in this example, there's only one input, but if this transaction had more than one input, then the script would be able to see those as well. There's one last ingredient that Plutus scripts need in order to be as powerful, as expressive as Ethereum scripts, and that is a so-called datum, which is a piece of data that can be associated with a UTXO in addition to the value. So at a script address, like in this example, in addition to this 100 ADA value, there can be an arbitrary piece of data attached, which we call datum. And with this, we can actually mathematically prove that Plutus is at least as powerful as Ethereum. So everything, every logic you can express in Ethereum, you can also express in this extended UTXO model that Cardano uses. But it has a lot of important advantages in comparison to the Ethereum model. So for example, in Plutus, it is possible to check whether a transaction will validate in your wallet before you ever send it to the chain. So something can still go wrong. So for example, your transaction can consume an output, and then when it gets to the chain, somebody else has already consumed that output. This output has already been consumed by another transaction. You can't prevent that. But in that case, your transaction will simply fail without you having to pay any fees. But if all the inputs are still there that your transaction expects, then you can be sure that the transaction will be validated and that it will have the effect that you predicted when you ran it in your wallet. And this is definitely not the case in Ethereum. In Ethereum, in the time between you constructing a transaction and it being incorporated into the blockchain, a lot of stuff can happen concurrently, and that's unpredictable. And that can have unpredictable effects on what will happen when your script eventually executes. So that means in Ethereum, it's always possible that you have to pay gas fees for a transaction, although the transaction eventually fails with an error. And that is guaranteed not to happen in Cardano. In addition to that, it's also easier to analyze a Plutus script and to check or even prove that it is secure, because you don't have to consider the whole state of the blockchain, which is unknowable. You can concentrate on this context that just consists of the spending transaction. So you have a much more limited scope, and that makes it much easier to understand what a script is actually doing and what can possibly happen or what could possibly go wrong. So this is it. That's the extended UTXO model that Plutus uses. So to recapitulate, in extending the normal UTXO model, we replace public key addresses from the normal UTXO model with scripts, Plutus scripts. And instead of legitimizing the consumption of UTXO by digital signatures, as in the simple UTXO model, arbitrary data, that's called redeemer, is used on the input side. And we also add arbitrary custom data on the output side. And the script, as context, when it runs, sees the spending transaction, the transaction 1 in this example. So given the redeemer and the datum and the transaction with its other inputs and outputs, the script can run arbitrary logic to decide whether it's okay for this transaction to consume the output or not. And that is how Plutus works. And that is, of course, not tied to a specific programming language. I mean, what we have is Plutus, which is based on Haskell. But in principle, you could use the same concept, the same UTXO model with a completely different programming language. And we also plan to write compilers from other programming languages to Plutus script, which is sort of the assembly language underlying Plutus. So this extended UTXO model is different from the specific programming language you use. In this course, we will use Plutus, obviously, but the understanding the UTXO model is independently valid from understanding Plutus or learning the Plutus syntax. When I planned this lecture and the course, I first thought I should do it the traditional way of starting very simple and maybe give a crash introduction into Haskell, then do some simple Plutus contracts and slowly add more complicated stuff. But then I decided it would be more interesting, especially for the first lecture, to showcase a more interesting contract and just demonstrate what Plutus can do, and then use that to look at certain concepts in more detail and explain them in more detail. So the code for this course will be in this GitHub repository. It's at input output HK and then Plutus Pioneer program. And here I have a clone of that repository. And I go into the code week 1 folder and do a Cabal build. In my case, everything is up to date already because I built it before, but when you clone the repository and do it for the first time, it will probably take a couple of minutes because a lot of Plutus libraries will have to be built. Let's have a quick look at the code. So that's in source week 1 English auction. And I don't expect you to understand any of that. I just want to show you that it's reasonably long contract, but not too bad. So let's see. Right, so it has 368 lines. And we see it builds, so that's good. So it compiles. Now I want to take this code and run it on the playground. But I don't want to use the official playground that's public on the web because that is a bit outdated by now. That's from end of January and Plutus has evolved since then. So I want to start a local playground server and try this contract on there. And for that, it's important that I use the correct version that this repository is also using. So we can check that we look into the Cabal project file. Here is the reference to the Plutus repository. And here we see this tag. So now I'm in a local clone of the Plutus repository. And I can check with git log that this tag here, that I have checked out the right commit corresponding to the one specified in my Cabal project file. So now in order to start the playground server, I need a Nix shell. So I start Nix shell and it takes a bit to set that up. And actually I need a second one. So I have another tab here in the same repository and I start Nix shell there as well. Let's switch back to the first tab. Okay, there's my Nix shell. Now I change into the Plutus Playground client folder. And there I now in this Nix shell have the Plutus Playground server command available, which will start the playground server as the name suggests. So this should be running now and it's running on port 8080. Now I switch to the other tab. There I also change into this Plutus Playground client folder and do an npm run start there to start the client that talks to the server. Okay, now the client is running and that is running at localhost 8009. Now I open my browser and go to this address, localhost 8009, and if all goes well, then the editor, the code editor should open. There can be some example contract there, which we can delete. And now we can just copy paste the code from the Plutus Pioneer program into this editor. So I just open this in a text editor and copy everything and paste it here in the editor. There's one thing we have to do in order for it to compile in my Plutus Pioneer project. I added a proper Haskell module header, But the playground doesn't expect that. It expects code without the header because it adds its own wrapper around it to actually run it in the playground. So I delete this module header. Then I press compile and have to wait a bit. And it should compile because I made sure that I'm now running it against the exact same version of Plutus that I also did the Cabal build against. Now we can switch to the Simulate tab, where we have simulated wallets and can script invocations of the contract and see what happens. So by default there are 2 wallets, but to make it more interesting, I add a third one. And this example script I wrote is an auction script, and the idea is that somebody can auction a non-fungible token. So we have a simulated one here, T, but the way it's set up by default is that every wallet would get 10 Loveless and 10 coins of this token. And then, of course, there would be 30 coins in total, so it wouldn't be non-fungible. So to simulate a non-fungible token, I give the first wallet exactly 1 coin and the other 0 of this. So now it's really basically non-fungible. It only exists exactly once. And the idea is to use this contract so that wallet 1 can have an auction, run an auction for this non-fungible token. Okay, and in my contract I defined 3 endpoints: start, bid, and close. So these 3 come from this contract. The pay to wallet is always there by default in the playground to do a simple transfer of Loveless from one wallet to another. So we can now add actions and see later then when we press evaluate how that gets evaluated in the simulated blockchain that the playground provides. So we set up the auction with start, and then we can enter parameters. So the first parameter get slot is the deadline of the auction. So the idea is that bidding only happens until a specified deadline, until a specified slot, and after that the auction is over. So for example, I can put slot 20 here. The second parameter is the minimal bid. So probably, I mean, at least in a real scenario, the seller of the token wants at least a certain amount of Loveless. And if nobody is willing to bid that minimum amount, then the auction just fails and the seller gets his token back. So just as an example, let's put 3 here. Of course, 3 Loveless is a very tiny amount of money, but it's just easier to keep the numbers small to see what's going on if there are not too many zeros. In a realistic scenario, there would be many, many more zeros, of course. And the next 2 parameters in the start endpoint of the contract specify the token that's sold. So we have to specify this token T here. And in Cardano native tokens, a token is specified by 2 things: the so-called currency symbol, which we will talk about a lot more later in this course, and the token name. And for some arbitrary reasons, the currency symbol in this case is 66 and the token name is T. Right, so this will now start the auction. Then we can also insert wait actions so that nothing happens for a couple of slots. So let's just wait for 1 slot to give it time to set everything up. And now bidding can start. Let's say wallet 2 and 3 both want to bid for this token. Let's say wallet 2 is faster and bids 3 Loveless. So wallet 2 invokes the bid endpoint. This takes 3 parameters. The first 2 specify the token, so that will be the same as here, the 66 and the T. And the third is the bid. So we specified a minimum bid of 3. So let's say that wallet 2 is willing to bid, to give this minimum bid. So after that, let's insert another wait action. Now let wallet 3 also make a bid. Same parameters as before, so 66 and T, and now the bid. So obviously the bid must be higher than 3 for it to be successful. So let's say 5. That's another wait action. And let's say that these two bits are the only two bits, or the only bits in the auction. So now we wait until slot 20, until the deadline. So now the auction is over, and now anybody can invoke the close endpoint to settle the auction. So if it was successful, if there was a bid at least as high as the minimum bid, then after the deadline is reached and close is called, the seller should get the bid, the highest bid, and the buyer, the person that made the highest bid, should get the token. And if the auction failed because nobody was bidding, then the seller should get his token back. So it doesn't really matter who invokes that, but wallet 2 would have no incentive to invoke the close action. It's only wallet 1 and wallet 3 that want something. Wallet 1 wants the bid, and wallet 3 wants the token. So it doesn't matter. We can, for example, say that wallet 1 invokes close, and this as parameter just takes the token, so the 66 and the T. So all these parameters and the endpoints are defined and specified in the Haskell code that I briefly showed you earlier. So I'm not sure whether we need another wait action, but we can just add one slot just to be safe. Okay, and now if we're happy with this scenario, the simulated scenario, we can push the evaluate button and wait a bit. So now the blockchain is simulated, and these wallets are simulated and their transactions. Okay, and it seems to have worked. And now we get this simulator view where we see every transaction that happened. So it seems there were 5 transactions that happened. The first one is not one that we specified by our actions. That's the Genesis transaction, the very first transaction that sets everything in motion and that distributes the initial funds to the wallets. So the Genesis transaction is special. It has no inputs. So the money basically comes out of thin air. And we see the total available money in the system, in the simulated system, is 30 Loveless and this one simulated non-fungible token. And this transaction has 3 outputs to the 3 wallets, and each of the 3 wallets gets 10 Loveless, and the first wallet gets the token as we specified in the previous tab. Okay, let's look at the first transaction. That should be the one where wallet 1 sets the auction in motion by calling the start endpoint of the contract. So this has 1 input and 2 outputs. The input is the only UTXO that wallet 1 has. So even though it's 2 different tokens, Loveless and the T, they sit combined in one UTXO. And as we discussed earlier when I explained the UTXO model, UTXOs always have to be consumed completely. So this whole UTXO is input to the transaction, but then there can be change output, as is the case here. So we didn't add any fees to our auction. So these 10 Loveless that wallet 1 has is change. So the first output is change where the 10 Loveless go back to the wallet. And the second output is more interesting, and here for the first time we encounter a script address. So this wallet 1, wallet 2, wallet 3 are just ordinary public key addresses. But now the second output of this transaction goes to a script, and that script is the one I define in the code, the auction script. So in this example we only have one script, only one smart contract that handles all the scenarios, the starting, the bidding, and the closing. And we see that the value at that script output is the token. So after this transaction, the starting of the auction, the token is locked in the script. And as we know from the introduction into EUTXO, there can also be datum, and there actually is datum, but that is not visible in this display. Okay, so now the auction is set up. So let's look at the next transaction that happened. That is when wallet 2 makes a bid of 3 ADA. So we have this transaction, and it has two inputs. It has the script, the auction script with the token as input, and the UTXO that wallet 2 owns. And afterwards, we have two outputs. The first one is change output to wallet 2. So remember, wallet 2 wanted to make a bid of 3. So 7 is change, that is here. And then the new script output still contains the token. It is still locked in the auction script. And it now additionally contains this bid, the 3 Loveless. So this this transaction consumes this UTXO, the script UTXO, and produces an output that again goes to the auction script. And of course, the code must make sure that nothing can go wrong here. So that, for example, wallet 2 can't just take the token. So the validator, the validation script here will make sure that this transaction only validates if there is an output where the token actually ends up in the script output again. Remember, in the ETXO model that Cardano uses, the script can see the whole transaction. So all this is visible to the script, so it can check that everything is well and that the token is not taken out of the script, is put back in the output, plus the bid that has been made. And now let's look at the slot 3, the next transaction. That should be where wallet 3 now bids 5 ADA. So that it's even more interesting. So the input side looks similar. So the original UTXO of wallet 3 go in, and the UTXO locked at the script with the token and the first bit, the 3 ADA from Loveless coming from wallet 2. Now the first output is the change, which in this case is 5 Loveless. The second output is now the updated script. So the token still sits there, and the new bit, the 5 Loveless are there now. And now we have a third output where wallet 2 gets its bit back. So wallet 2 has now been outbid. Wallet 2 had a bid of 3, and now wallet 3 makes a bid of 5. So by bidding 5, wallet 3 has to pay back the original 3 Loveless to the original bidder, wallet 2 in this example. And again, the logic in the script, the code must make sure that all of this is handled properly, so that wallet 2 indeed gets the bit back and that the token is still locked in the script. And of course, the code also must check that this new bit, the 5, is indeed higher than the original 3. Okay, and now the last transaction is the close at slot 20 after the deadline has been reached. So let's look at that. So this only has the script UTXO as input with the token and the highest bit, which is 5 in this example. And it has two outputs. So wallet 1 gets the 5 Loveless, the highest bit, and wallet 3, the bidder that made the highest bid, gets the token. And we can scroll down a bit to see the final balances, and we see that we have the expected result. So wallet 1 doesn't own the token anymore, but has 15 Loveless. Wallet 2 is back to 10. During the bidding for a while, it only had 7 because it had made a bid of 3, but it got that back when it got outbid by wallet 3. And wallet 3 now only has 5 Loveless left because it paid 5 to the seller, but is now the proud owner of the token. We can also briefly check what happens if something goes wrong. So for example, if wallet 2 makes a bid that's too low, that's below the the minimum bid, and let's say wallet 3 makes the same error. So in this case, these two bids should be invalid, and the auction should fail, and in the end, the seller, wallet 1, should get the token back. So let's see. Okay, so now we see we have only 3 transactions. Again, the Genesis transaction, that's the same. The start is also the same. But now the biddings don't happen because they are not valid. Because there's logic in the Haskell or Plutus code I wrote that checks that, for example, the minimum bid is respected. And so in this case, because the 2 bids were too low, 2 ADA, where the minimum bid was 3, they are not accepted into the blockchain. And then the last transaction is just a closed transaction. And this is now a failed auction because there was no bid higher than the minimal bid. So it takes the script output and just gives the token back to wallet 1. So as a result, we get the same as after the Genesis. So that scenario also works of a failed auction, that in the end, the seller gets the token back if there was no bidder. So if we scroll down, we also see log messages. And for example, here we see bid lower than minimal bid. So that's an error message that I built into the code that helps debugging. So we see not only that the transaction failed, but also get a reason why it failed. So there you have it. A relatively complete and relatively realistic auction written in Plutus as a Plutus smart contract. So coming briefly back to the code, as I said before, I don't expect you to understand the code now. But when writing a Plutus contract, it's important to realize that there are 2 parts to a contract. The one part, the arguably more important or most important part, is the script that basically lives on the blockchain and that governs which inputs can be consumed by a transaction and under what conditions. So that has to be specified, of course, when you write a Plutus contract. But the other part, which is maybe equally important, is that wallets have to be able to create transactions that then will be validated. So on the one side, you have the script that locks the UTXOs and makes sure that they can only legitimately be unlocked. But in order to actually use such a script output and use it as input to a transaction, the wallet must be able to create transactions that fulfill all the conditions so that the script will be happy to allow the transaction to consume this UTXO. So therefore, there are 2 parts to a Plutus contract. The one part that defines the validation that happens on the blockchain, and the other part that allows wallets to interact with this contract. And the nice thing about Plutus is that everything is written in Haskell, and in particular, the data types can be shared amongst the 2 parts, the on-chain and the off-chain part. So if we briefly look at the code, so here in the beginning, for example, I define a Haskell data type that defines an auction, the address of the seller, the deadline, the minimum bid, and the token that's being auctioned. And you will recall that that corresponds exactly to the parameters of the start endpoint that I showed you in the playground. So then there is some Haskell stuff, just defining a couple of data types. And then this part here, this is actually the logic that defines the script that lives on the chain, the validation logic of the script. So here are all the conditions encoded under which circumstances this script output can be unlocked. So this goes until about here. And here actually the actual script is defined. So this auction instance is the script, the auction script. And then from here, this is now the wallet part. So these three data types, Haskell data types, define the parameters of the three endpoints. And here are the three endpoints, the logic of the three endpoints. So this is the logic of the start, which constructs a transaction that starts the auction. This is the logic, the bid endpoint that controls how bidding works and how to construct a transaction that can do a bid. And finally, here's the logic that defines the close endpoint. The nice thing that about everything being Haskell is that the on-chain part and the off-chain part can share code and can reuse code. For example, in the logic for the bid, at some point I have to check that the bid is valid, and in particular that the bid is not too low. So there's this sufficient bid helper function somewhere. And that uses a function min_bid, which basically decides in every situation what the minimal valid bid will be. So that's defined here, up here. But the point that I'm trying to make is, so this is used, this function min_bid is used when I write the script that lives on the blockchain. But if we go down to the bid endpoint, the min_bid function is also used here, because the wallet also has to decide whether the bid is high enough or not. It doesn't really have to. It could just do the bid anyway, and then the transaction would fail. But of course, it's nicer if the wallet immediately checks and refuses to even try to create this transaction, because it will fail anyway. So there are often situations like that where logic is shared between the on-chain and the off-chain part. And because both are written in Haskell, it's very easy to share code like this. And that also makes it much easier to keep the on-chain and the off-chain part in sync. Right, and the rest is just boilerplate. It defines the endpoints here, so that this is where the names of the endpoints come from: start, bid, and close. And they're here just associated with these functions: start, bid, and close. And the rest is just these last lines are basically just for the playground in order to set up my example token. So this is this token I used as an example that was auctioned away. So I hope you enjoyed this walkthrough through the auction contract and are excited to learn how to do things like that, or even more interesting things like that yourself during this course. And that's the end of today's lecture. So all that remains is homework. So I plan to give you a little bit of homework every week so that you can practice, because in learning a programming language, it's always very important that you try it yourself. Because often, if you listen to a lecture, even if you think you understand everything, then if you sit down and try it yourself, you actually realize if there are certain things you didn't really understand as well as you thought you did when you listened to it. But of course, we haven't really learned anything yet, so I can't ask you to write a simple Plutus contract. So for the first week, I would just like to ask you to basically do what I did in this walkthrough. So clone the Plutus Pioneer program repository, get it to build with Cabal build, clone the Plutus repository, check out the right commit, get the Nix shell working, start the Plutus Playground server, start the Plutus Playground client, then copy paste the code from the Plutus Pioneer program repo into the playground and make it compile, and then simulate some auction scenarios. So it would be great if all of you could manage to get that working, because then it means that your environments are properly set up and we are ready to tackle more interesting things. So that was it for the first week. Thank you very much again for attending the course, and talk to you next week. Thank you.